And also, if you have questions, either two ways, you can write them in the chat, or you can open your mics as well at the end. So I'd like to please ask you to hold your questions until the end, if possible.
Sorry. Oh, Matthew, I'm fine if they ask during
during the presentation.
During the presentation, that's fine.
Okay.
If anybody has a question or requires clarification as we go through the slides, please just open your mic and ask the question, because I don't see when the presentation's on, I'm not seeing what's in the chat, so I just keep on going on. So that's easy for me.
Okay.
All right.
Perfect.
I'm gonna turn my camera off now just to save bandwidth, and I'll open up the slide deck.
Great, thanks.
Okay. So welcome everybody. Oh, it's only the main slide. Okay, that's fine. And thanks for spending the next 45 minutes to an hour with me today. Matthew asked the presentation about variable speed pumping. I'm going to make this as agnostic as possible, because first of all, variable speed pumping is agnostic. But as I go through, I'm going to be talking about, one of the technologies that's in the industry, which refers to what we refer to as sensorless control. The point I want to make here is that though Armstrong was instrumental in introducing this type of technology to the marketplace, our competitors offer the same type of technology as well. So being it a Taco pump or a Bell & Gossett Xylem pump, the way sensorless technology is done is more or less identical. But the point here is that as we go through this, I'm just trying to build up so that everybody has an understanding of how this is developed, why it's developed, and how actually on the commissioning side, it really is a problem solver when the application or the technology is applied in a number of different systems. And we can talk about that at the end of the presentation if anybody has any questions. So without further ado, first of all, variable speed pump control. So the agenda today is, first of all, we're going to go through ASHRAE 90.1 and its application to variable speed pumping, a review of the affinity laws, and then the pump system and pump control curve, which is basically covering second-year fluid dynamics for those of us who are mechanical engineers. Then a review of how variable speed pumping works in a system, and we'll be covering an understanding of the methods of controlling flow. Then we're going to go through an explanation about how sensorless control works. And after that, efficiency-based staging, what is it as it applies to parallel pumps, and then a little bit of a discussion on pumping capacity redundancy and the difference between redundancy and N+1 design. So, and at any time, if anybody has a question, please feel to ask. So, first of all, if we look at the industry as a whole on the HVAC side, historically, we've always been operating in a constant speed, constant volume mentality, and we've been designing our pumps based on a design point efficiency at peak load. Whereas as we've gone through, we understand that almost 90% of the time, our pumping equipment actually operates at part load. And so with that understanding of part load, there has been a focus now for the last 20 years plus of moving away from a constant speed, constant volume mentality to sizing your pumps based on part load operation and understanding maybe we should be looking at best efficiencies at part load, not at design. Part of this then was that back in around 2007, ASHRAE came up with 90.1, which is an energy standard for buildings. Now, today, the National Energy Code of Canada for buildings, NECB 2015, is harmonized with ASHRAE 2013, and it provides the minimum requirements for the energy efficient design of buildings. In the US, 49 states have adapted anywhere from 2004 to 2016, and then California has its own Title 24, Part 6. Currently, ASHRAE is, the codes are moving to 2019, but I believe ASHRAE now is going to be issuing 2021 or 2022. I'm not sure about that. But if you look at that, one of the things that what we focus on is hydronic variable flow systems. And what ASHRAE was saying is that individual chilled water pumps serving variable flow systems having motors exceeding 2 horsepower or 1.5 kilowatts shall have controls and or devices such as a variable speed control that will result in the pump motor demand of no more than 50% of design wattage, no more than 30% of design wattage at 50% of design flow. So that's a lot of verbiage. And I always say, well, what does that really mean? So basically, what Ash was saying is that you need to have a control valve that's capable of reducing the system flow to 50% and less of the design day flow requirements. So a valve reducing the flow to 50%. When we reduce that flow by 50%, the energy being consumed is reduced by 70%. And this is being done by using a differential pressure sensor or some other control device that is located or mimics the most hydraulically remote load in the system. And so I always ask, when I'm doing my lunch and learns is where did ASHRAE come up with this? And quite simply, all of this is based on fluid dynamics and specifically the affinity laws. And I stop at this slide because there's a lot of information. And if you remember the affinity laws, everything that we're going to talk about builds on the next 2 slides. Now, first of all, the affinity laws tell us that there are 5 variables that define a pump's operation, those being the impeller diameter, the head, the flow, the speed, and the brake horsepower. Now, what ASHRAE is saying is that when we reduce the flow, we should drop the energy by 70% at 50%. Well, that's just following the affinity laws. Drop the speed by 50%, the horsepower drops by the cubed of the squared. And that's where you're going to get your energy reduction at part load. On top of that, we also need to understand, oops, hit the mouse, sorry about that, is this red line, and that is the control curve. Now, historically, if you had a pump operating at constant speed, constant volume, constant speed, you are running on the blue lines. And as a valve chokes off, you move up on that blue line, and that is your new flow. But the reason you have that adjusted flow is because you're controlling on pressure or head, changing the resistance. The other way you can adjust flow is with the impeller trim. When you go to variable speed, you are running on what is referred to as the control curve. And what's important here is that the way the control curve is determined is that, first of all, you will have your design point, which is when all valves are open, and then you will have your minimum system pressure at 0 flow. And what's important about understanding this point here is that this point is determined by where the DP sensor is located in your system. And we're going to cover that in a bit more detail in the next few slides. But the point being here is that understanding how the control curve is determined and how it is set up in a system is paramount into understanding, first of all, variable speed pumping, and then how sensorless control works. So a lot of times what I find in the industry is that engineers will confuse the control curve with the system curve. And just remember, the system curve is a function of the system as water is moving through the piping network. And as you know, it's exponential, right? Flow increases, the resistance increases by the square. So where the system curve crosses the control curve at a certain speed is where that pump is operating. And everybody, if I will provide this slide deck to anybody who wants it after this presentation. So now, how are pumps traditionally controlled in variable flow? Well, a traditional system has a DP sensor, a drive, and a pump. And the way this DP sensor works, and this may be, I'm repeating this to everybody, but it's fundamental to understand this, is that the DP sensor basically has a diaphragm in the middle. And it has pressure ports on both sides. When that sensor is at a zero set point, i.e. the pressures on both sides are the same, you have equilibrium in the system. As a valve opens or closes in the system, that pressure changes from one side to the other, and there's a set point deviation, either positive or negative. So that sensor picks up that deviation, sends a signal to the controller, which is the drive, and the drive then either speeds up or slows down the pump to get back to that zero set point. The key in all of this system, or in this traditional configuration, is that we don't know what the flow is unless we have a flow meter. The drive does not know what the flow is. All it knows is that there's a deviation from set point. I have to speed up or slow down. So it's very much traditional closed loop, but not embedded with technology or intelligence. So that's our traditional system. Moving forward now, traditional systems, typically there are three areas where the DP sensor will be located. See a lot of installations where the differential pressure switch is located in the mechanical room across the supply and return of the pumps. ASHRAE is mandating that it's installed in the most remote load in the system. A lot of engineers will specify 2/3. So you're locating that DP sensor at the 2/3 point. And so now these are the variances, and this is key as you go through in understanding, is that when that DP sensor is located in the mechanical room across that supply and return, basically what that means is that when I have a zero set point, I have to have the same pressure on one port as to the other port for equilibrium. What that means then is that at minimum flow, my pump still has to generate all of this head pressure to have that set point at zero. What that means, so I have to pump all the way through here or generate that pressure to get that to have a zero set point. The control curve then is a very flat line, which is almost like constant pressure. And the end result is that we're not able to achieve ASHRAE's mandate of a 50%, 70% power reduction at 50% flow, because we're operating way up here. When ASHRAE mandates that that DP sensor is located at the most hydraulically remote load, what that means then is that at zero flow, we only need to have the head pressure from here to here for that to be in equilibrium. The end result is that now at lower flows, we can actually drop the speed significantly more because our control curve is much more of a quadratic. And the end result is that at 50%, we're way down here and we're achieving those energy savings. The challenge with this sometimes is that on more complex systems or with multiple risers or multiple runs, when we install that DP sensor at the most hydraulically remote load, we stand a chance of, at low flows, not generating enough head to satisfy zones that are closest to the mechanical room. And you hear this quite often in some of these systems of, I'm not getting any flow in some of my zones. So what engineers do to minimize that is that they are actually moving that DP sensor 2/3 of the run. And what that does is that it bumps this value of the control curve at minimum flow up slightly. And then hopefully we're meeting ASHRAE 90.1, but we're resolving issues of no flow at zones closer to the mechanical room. So that's how that configuration works. The other challenge now, though, is that once the DP sensor is located in the system, it's fixed. And if it's in the wrong location, you have to basically drill, tap, find nucleation, and then run your conduit and your wiring at that new location. So it becomes very much of a hard-pressed or a fixed application in the system that doesn't lend itself to adjustment as if there are issues like zero flow or starving points of the system.
Excuse me, Andrei. There's
Yeah.
a hand raised on this
Okay.
slide, I think. There's a question.
Thanks, Andrei. The question I have is, you said that in the closest load to the mechanical room, we are not going to have flow, whereas we are going to have enough flow in the furthest point. How does it happen? I can't get it.
Okay, so basically what happens is that I have my DP sensor located here. So this think of the best analogy I would have is that in your house, you have a thermostat. And if you put the thermostat on the second floor of the house, that means that the thermostat is registering the temperature at that second floor. Now, you may go to the main floor and it's not, if it's a heating application, it may be too cold on the main floor, but the upper floor is satisfied. So when that DP sensor is there, it's controlling the system. What happens then is that this may be my minimum head pressure, but at zero flow, I may need, let's say that this is 10 feet, okay, at zero flow, I'm good. But at this point right here, I'm going to need 15 feet to go through this loop. My pump says, oops, I'm satisfied. Good. Sorry. My control curve, my DP sensor says I'm being satisfied, but this zone is not getting any flow because I'm not generating enough head to get to here. So what you need to do is you start to move this line up. this control curve, which basically says that I'm moving the speed up until I have enough to get to that zone. And that's why if you see in a lot of buildings, a lot of times what you'll find is that if there's a riser or a fan coil that's not being satisfied, it's typically one that has the lower flow, we're not generating the head pressure to get to that zone.
But that's not something that we need to check during the commissioning of the project when the balancer is coming, and to give us that number for DPS set point, that to look at all different zones and risers, make sure that at any certain set point, everywhere is getting enough flow. That's my question one. And question two, that scenario can happen in any other location, not necessarily closest to the mechanical, right?
Yes, you're absolutely right. It can happen in any other location. The point being is that once the DP sensor is located in the system, and if there are issues, that DP sensor is fixed. So you have to relocate that DP sensor if you can't calibrate it to deal with that issue. Okay, so that's where it becomes a challenge. Outside of this, as we get to the end of this, I'll give you an application of where we had something, a challenge like this for a Toronto housing a project ourselves, where they incorporated the DP sensor and they located it at the most hydraulically remote load in the system, and two of the risers weren't being satisfied, and so as we go through, I'm going to show you how the sensorless technology was able to address that at the panel without having to worry about the mechanical location. Okay. So let me go to the next slide just to show you about the sensorless side, so that it pulls it all together. And then we can have that conversation at the end.
Yeah, thanks.
Thanks. Okay. So moving forward, now we move into an integrated solutions technology. And basically, when we talk about sensorless control, I'll go back to, first of all, explaining how sensorless control works. First of all, as I said in the beginning, every single pump operates based on the affinity laws. And there are 5 variables that define a pump's operation: the impeller diameter, the power, the speed, the head, and the flow. So if you look at this pump curve right now, and we're operating at this duty point right here, we're going to get 1,000 GPM because there's 80 feet of resistance in the system and we're running at around 1,600 RPM. If a valve closes, we start creeping up on the blue line right here, right? The speed line. And that DP sensor registers a change, an offset or deviation from set point, and then the drive starts slowing down and we get back onto the control curve when we meet that 0 set point again. We're at a satisfied situation. At the same time, when we are operating at this point right here, we are generating, or the motor requires a certain amount of power to move that fluid. And as that valve closes, the power required changes. So basically, what we're doing in sensorless control is that we are just controlling to a different variable. Instead of controlling based on pressure, we are now controlling based on the power required for the motor. And I'm going to stop here to give you a lot of times people ask, well, how does this work? Now, first of all, in our industry, every single centrifugal pump we uses what we refer to as a variable torque motor. And a variable torque motor, basically what that means is that that motor will only do the work required based on the resistance of the shaft. And it will only draw the power required to overcome that resistance on its shaft. So if I have a 200 horsepower pump, and just for the sake of making this simple, and we'll use a linear relationship, we'll say that a 200 horsepower full load amps is 200 amps. If there is no
I'm not dealing with
load,
this shit anymore. Nav can fuck himself. Actually, he can't. That's half the problem. He can't get it up.
Yeah.
oops. Sorry. If you look at the load on the shaft, and you've got variable torque, so what happens is that now the power, it'll only draw the power required based on the resistance on or the load on that shaft. So if that 200 horsepower motor only has 1 horsepower worth of work to do or no load on the shaft, it's only going to draw 1 or 2 amps. And as the load or the resistance on that shaft starts to increase, the amount of power that's being drawn to overcome that resistance starts to increase. So we are using that function or understanding that function in how we're operating sensorless control. And the way it's done then is that what we're doing is we're tracking the power that's being drawn by the motor and the speed of rotation it's at. And based on that power and speed, we have that equated to a flow and a head. The way this looks then is that basically we're creating a matrix in the pump, and we run that in the factory. They run that pump at a series of speeds, and then they plot the data. And what they're plotting is the flow to head at different speeds, and then the flow to power at different speeds. So you have this matrix of data that basically looks like this. So we've run the pump at a bunch of different speeds, and at those different speeds, we take the flow, the head, and the power consumed. And as you can see, as the flow increases, the power changes. So now we have this matrix of data. All we're doing is overlaying the control curve. So now we define this. Basically, it's a quadratic equation, and this is where we're running at. And we determine then the design point, which is what the design of the building, and the minimum system pressure we typically specify at 40% of design. Control curve is calculated, and now all the controller knows is that it needs to run on this red line at any time. So if there's a change in the system, it just looks, we've deviated from this red line. What are the data points? We get back onto that line. Okay.
Andrei, there's a question.
Go ahead. Yeah.
Andrei, I just had that question. You said that the pump can be calibrated, as it were, in the factory to build that matrix of flow versus power, right? When we take this pump and we install it in the field, two questions. Would those parameters change at all because of situational effects being on the field? And the second question is, now that we have the pump operating and controlling our system, over a period of time, like years, 5 years, 10 years out, do those parameters change? Does the pump performance with respect to those parameters change in any way over the life of the pump?
No and no. So the way this is done is that at the factory, we have a calibrated flow meter on the test rig. So this is that the data points come directly from a calibrated flow meter in the factory. And the end result is that the accuracy of the flow meter is within 3 to 5%, just like the calibrated just like the calibrated meter. So you're actually using a calibrated meter to take these data points. And simply because of our industry, we're typically moving water or glycol in our system. So we don't see wear on the impeller or the volute over time that would degrade the data points in the system. So yeah, so that's, and right now in the industry, we have pumps that are running like with this type of technology, God, introduced in 2007, so like 15 years. Yeah, and there's no change in the operating parameters on the system. So it's a good question, and it's been asked quite often. But yeah, because we calibrate against we collect the data against the calibrated meter, it's as accurate as the meter in the factory, which is to 3 to 5%.
Thank you, Andrei. And just one quick follow-up question.
Yeah.
I'm assuming that these numbers is for a specific fluid. So like if we change from water to glycol somewhere along the life of our system, this would have to be recalibrated, correct?
No, it won't be recalibrated. We would just put the density factor against this data point. So we typically we test against water all the time, and then we will add the correction factor if it's 10%, 20%, 30% ethylene glycol or propylene glycol as well. And that's a parameter. So to your point, you could have this pump in the field, and if the fluid changes, you're just changing the constant factor for the density of the fluid in the controller itself. It's actually a parameter that can be changed in the card. It's just something that we don't cover right now. I'll take an aside right here. I'm going to take my Armstrong hat off and be agnostic. So we have, when we first developed this technology, we used Danfoss's VLT drives. We still use their chassis. We've just because we've added other features, we have our own control card. Takeo and Xylem are still using Danfoss's integrated control card in there, and so it's a parameter in there in terms of changing the density of the. Okay. So,
Okay.
and that's the beauty of this is that it's all menu driven on the drive. Okay.
Thank you, Andrei. That was my question.
Okay.
Andrei, there's another quick question.
Go ahead.
Yeah. Okay. I'm sorry. So I was wondering, how do you measure the RPM of the pump?
Oh, the RPM is just measured from the drive itself. It's taking that rotation. The frequency right there.
The frequency. So there's no sensor, like rotational sensor on the shaft of the pump. There's nothing like that.
No, there's nothing like that. This is like the drive is going to read this itself, and it just equates that frequency to the speed itself.
Okay, thank you.
Okay, all right. So, but that's basically how the technology works. So, understanding first of all, it's a variable torque motor. That's why, and the torque required changes with pressure and flow and speed. So once you can visualize this, it's basically a lookup table, it's a matrix, and then you're overlaying the control curve on there. So what's beautiful about this, first of all, is that now you can just through parameters on the control card, you can dictate whether you want a quadratic curve control, whether you want constant flow control, so basically a straight line, or you want constant pressure, in your system, or you can adjust this accordingly. So you're no longer fixated or held to the DP sensor's location. You can adjust this at any given time. And it's just parameter driven on the control card, right? The other thing now is that the data output, now this is the Armstrong version, but the Danfoss, the VLT drive has the same parameters. You'll have flow as an output, you will have head as an output, you will have speed, power, voltage, and current. All of those data points are being read from the drive, and they're visual. So the beauty about commissioning is that when you are setting up the pump, instead of trying to look at a pump curve and validate flow, you actually have the validated flow value right at the drive, right there. You're reading it, so you know what's going on, which really, and I've been in projects where they're very complex, where you got primary, secondary, and you're just looking and you're validating. You can see what the flow's going on. Also, there's a function that's available that's called auto flow balancing. And what we typically know of our industry is that engineers will always overestimate the head in their systems. It's just it's easier to slow down a pump than to take a pump out and have to increase its size if there's an error in calculations. But when we have pumps that are oversized, typically what happens is when that pump is operating, it's going to operate to the right of the system. Auto flow balancing affords you the ability of just saying, this is what my design flow is, and it will balance the pump, i.e. adjust the design point speed based on the resistance of the system. So it gets you right back to where you need to be. And then it locks in on that portion. So that's the other functionality that's available in this type of technology.
Question, Andrei, on this
Go
one.
ahead. Yes.
Thank you, Andrei. You're actually bringing us down to the point of this sensorless pump. Thank you very much. The question that just I have is, when we are doing sensorless approach for pump control, in the lower flow demand, does the head decrease or remains constant?
Sorry, in the lower flow?
In the lower flow, let's say valves close, and then we have less flow demand. So the pump decreases the frequency. So does the head pressure decrease or not?
Yes, it does. So basically what's happening now is that what's happening in your system is as you start closing valves, right, you're decreasing the demand for flow. So now, as we decrease the demand for flow, we know that we don't have to run at a higher speed. So we start dropping the speed of the pump. As we drop the speed of the pump, the head, it is going to drop to that point where it meets what the resistance in the system is. So if all the valves are closed and so your resistance is still 20 feet, it's going to stop to where it's 20 feet and it's going to be moving that much water there. That's all it is. And it's funny you ask that, because it's like that's one of the fundamental challenges in understanding how systems work is that typically a lot of what we do today is still all based on pressure control. So we have valves that open or close, and those valves opening or closing adjust the pressure in the system. That pressure change is then dictated in terms of increasing or decreasing your flow requirements, right? Like if I've got a fan coil and I'm closing off a valve, I'm closing that valve because I need less flow. And I'm opening that valve but because I need more flow. When I open that valve to increase flow, I'm starting to move more water through that fan coil. If I'm moving more water through that fan coil, the resistance in my system starts to increase. So what we're able to do now is, instead of now being fixated once with a DP sensor, we can consistently adjust right at the control card, right across the board. And that's the beauty of this. Now, this is just like a 45-minute, 1-hour presentation to the technology. But, if anybody wants to do a deeper dive into it, I'd be more than happy to spend more time with you, because this is where this becomes very, very, it differentiates how we're pursuing systems today. And then all of a sudden, it really becomes more of an energy conversation in our design philosophies and how we're moving BTUs in the system.
Yes, Andrew, we
Yeah.
can discuss this after this, but just let me place my question here, because in traditional approach, when we had one differential pressure sensor at the end of the hydraulic line, so once the pressure was being kept constant, so if one unit, one load at the vicinity of the mechanical room closes, the flow actually decreases, but we keep the pressure or differential pressure constant, so the furthest hydraulic point still would receive enough flow or enough
That's
pressure.
right.
So,
Yeah.
but in this approach, since the head decreases, our furthest point may not receive enough flow only because the head pressure is not high enough.
No. So what'll happen is that the pump is always responding to the overall resistance in the system. So even if a valve closes, the way you have to visualize it is that with valves opening or closing, if my overall resistance is 60 feet of resistance or 60 feet of head, I am going to provide the flow based on that control curve to give you the flow that's required at 60 feet of resistance. Now, if at 60 feet of resistance, we're having an issue and not getting the flow we require, we are afforded the ability to adjust that control curve so that we can get that flow. That's what's really unique, or that's what differentiates this type of strategy or this type of logic. Like traditional is that when you have that DP sensor in that system, I always come back to it's fixed. Now, if you have a more complex system and you have multiple DP sensors, you are always controlling to the DP sensor with the greatest offset from set point. But then the challenge is that you're over pumping the other zones as well. So what this affords us is, and then and this starts getting into all other technology, but incorporating pressure independent control valves in this. But the beauty is now that we can always optimize the pumping energy based on what the system requires in the application at that point. So I'm hoping I'm not confusing too many people on this right now, because we're going off on tangents. But like I said, if anybody has questions for follow-up, please reach out, because there's numbers of applications that I can present to you, or where the technology is working and how we've resolved issues with this type of technology and stabilized systems. So I'm going to continue now with the efficiency-based staging side, because I think we've got 15 minutes left. I think I can squeeze the last two portions in the next 7 to 10 minutes, hopefully. So efficiency-based staging. One of the other functionalities now is that instead of the traditional staging of pumps based on speed, what we're able to incorporate is staging based on the pump's hydraulic efficiency. And what that means is that in traditional systems with BMS's controls, first of all, on a speed-based system, we know that a pumps can provide up to 90 to 100% of its design flow. And on a traditional system, we would take that pump, that DP sensor will send that signal, and we will continue to pump until we reach basically 90% of that pump's capacity. Whereas with efficiency-based staging, the efficiency of the pump is incorporated into the staging logic, so that what we do is we look at when that pump basically crests its peak efficiency and starts dropping down, we will stage the second pump on, as opposed to letting that pump run to its 90% point. And typically what that means is you may be staging your pumps anywhere around 50 to 65% of their design load, as opposed to running it to 90%. The reason this works is simply, if you look at the laws, power is equal to flow times head divided by 3960 times the efficiency. So the end result is that if you're staging your pumps at a higher hydraulic efficiency, you're using less power. So it doesn't matter whether you're running 2 pumps here as opposed to 1 pump. Because you're at a higher hydraulic efficiency, your overall brake horsepower is significantly less. And at this area, you can see up to a 15% power savings. Depending on the number of pumps you're operating in parallel, that power savings can increase to about 20% and up to 34%, depending on the size of the system. And then lastly, redundancy. One of the other challenges in our industry is that engineers typically will design their systems for 100% redundancy. And what that means is that we're going at an N+1. So we have 1 pump that is designed to do 100% of the flow. And then we have a second unit that's there as an idle asset. When we look at redundancy, though, what we're saying is that maybe it's easier to have 2 pumps operating in parallel, make the sizes slightly smaller, and actually determine what is the actual amount of backup that you need in your system, is the best way of describing it. So, because a lot of times we base our redundancy on flow requirements, but our industry is moving thermal energy. So if you're looking at it, we can go, for example, at a 50% capacity split, i.e. have, instead of an N+1, we have 2 pumps that are half, but we are still able to meet 70% of the flow requirement and 70% of the energy movement that we require. So if you're looking at energy savings, instead of 100% redundancy, going to 70% or 50% now becomes an opportunity not only to save on the sizing and the cost of the pumps, but on the energy consumption as well. So instead of doing 2 pumps, for example, at 20 horsepower each, we've done 2 pumps at 10 horsepower, 50% redundancy, but then it comes back to what we were talking about here in terms of those humps and the turn down capability. Now I'm afforded, because I have 2 pumps, I've actually increased my area of peak performance in our system. And we've improved our turn down capability in that system from 24% down to 12%. So, and that's it. I've got 8 minutes for questions. Yes.
So I think the first question is Kani.
Nope.
Oh, Mr. Riza, you still have your hand raised?
Yes, yes, yeah.
Okay,
Can you
go
hear
ahead.
me now? Okay, thank you. Andrew, the way that you explained, I think we can leave the staging or sequencing of the pump based on the lead lag or whatever. We leave it to the pump's controller instead of having BAS write a code for that.
Yes. Yeah, and that's exactly it. So that technology is embedded in the controls as well. In the practical sense, what happens is that you're basically daisy chaining the drives together, and they communicate with each other. So you're using the sensorless technology, and then you're incorporating the staging points as well. Okay.
Yep, thanks.
Okay, second question, Mike.
Yeah, Andrei, thanks for that great presentation. I learned a lot from it. The question on the last slide or the last topic you covered, which was with respect to redundancy. So if for our project, right, we we would have traditionally sized 2 pumps at 30 horsepower each, and using your methodology or approach, we decided to size 2 pumps at 20 horsepower each, right? In the event, and like facility owners are very wary of situations which probably will never happen but can happen, and that is that we lose 1 pump in the middle of at a design day. Would the smaller sized pump that we built our project on support the heating or cooling load on that very cold or hot day?
What you would find is that you're at 80%, depending on the redundancy you've built in. You will have anywhere between 80% to 95% still of the performance requirements in that system. Because what you got to remember is that going back to it, load is equal to flow times delta T, right? So if I reduce so what you're doing is you're reverse calculating and saying, what is my BTU load on that design day? And if I go to redundancy, what is my actual flow requirement? And then you do that calculation and you find out how many BTUs you're actually going to be moving. And what we typically find is that and I didn't bring this slide here and I can share it with you later, is that even with redundancy, when we're moving, especially on a heating system, we're still able to provide anywhere between 90 and 95% of the thermal energy required for the demand on design day. Okay, and if you want to reach out to me after this, I can provide those slides to you so you can visualize it. But to your point, it is a calculation, and it becomes like what level of I won't refer to it as risk, but there's the opportunity for energy savings in the system in there. And then, what is the statistical probability that the worst case scenario happens where you lose 1 pump on that design day? And if that is the case, really, how much cooling or how much heating capacity do you still have? All right.
Thank you, Andrei. That answered my question.
Yeah. And just to add to that, like, if you look at the practical sense of this, sometimes engineers oversize anyway. So, like part of our industry as commissioning agents is that I think all of us could make a fortune going into any building today and just seeing the, how oversized systems are. I'm working on a recommissioning on a major telecommunications company where we're changing all of their condenser water pumps after 8 years because we determined that there's a 3-year ROI on changing the pumps right out because they were all oversized and they're all operating on constant volume. So.
Okay, thank you, Andrei. There's a written question from Derek. You want me to read it for you?
Oh, sure.
For a parallel pump setup, why have I seen the IPS display showing both running at same speed, but one pump at very low or almost low GPM and the other was at design point? The piping, etc. looks identical, leading the parallel pumps. Should the IPS pumps be able to adjust themselves correctly? Is the controller different for parallel pump for VFD setup than duty standby rotation setup? So I think, Derek, this is a personal situation you had.
This is an actual application. So off the top of my head, I'd have to see what's going there, what's happening at the IPS itself. Because it comes back to the pumps are still responding to the load. And is it an issue of a piping configuration on the manifold itself that's resulting in imbalanced flows? I don't know. I can't, and without me being there, I can't answer that. But if you want to take this question offline, Derek, and bring, and we talk about the application. If I can't find the answer, I know somebody who can guide me through it.
Okay, thank you, Harry. So time's almost up. I don't see any more questions. So on behalf of all the attendees this afternoon and Eastern Canadian chapter, I'd like to thank you very much, Andrei, for this great presentation. So the recording will be available to all the members of the BCA.
Yes.
So thank you very much again, Andrei.
And Mathieu, I will send you a copy of the presentation. So if anybody wants it, they can reach out directly to you and get a copy. And I'll, my contact information is in there. If anybody wants to follow up or have any questions, please reach out. We're more than happy to help.
This is great.
Thanks for your time, everybody.
Thank you very much.
Okay.
Good afternoon.
Thanks, guys. Good afternoon. Cheers.
Thank you. Bye.
Thank you very much.
Thank you.
Thanks, guys.
Bye.
Thanks. Bye.